Hello folks, how's all doing? Hope you are coping with the lockdown and everything. And if you are feeling down, always remember, the Goonies never say die. So I'm going to go through this tutorial thing for you. And after I do this, I'm going to send you more questions that are kind of along the lines of the ones that's on the graded unit. They're very similar to these kind of ones, actually. Just a slight couple of wee differences here and there possibly. So I'll do this tutorial and I'll give you another one, then I'll go over it again in the next video. Then we'll go into something else. That's fair enough for dynamics really. So the other ones will be a bit more challenging than this one. But so I'm going to start getting into this. Okay, right, question 1. Right, into that. Okay then, I'm going to go into my other wee doodah thing, so... Right, question 1. Somebody hits a golf ball. It's kind of going to go like that. And it's going to land again. Up here is going to be its maximum height. And this is going to be its range. And that's its height. Maximum height. Right. So, and it's getting shot out at 7 meters per second at an angle of 40 degrees. The flight of the ball, the velocity of it is made up of two components. You have the horizontal velocity component and you'll have your vertical velocity component. And this is us back to our old friend Pythagoras, where this will be the cos part and this will be the sine part. So the horizontal velocity is equal to 7 cos 40 degrees and velocity in the vertical direction is going to be 7 sine 40 degrees. You see that? I'll write this right out a little bit better. That's 7 and that's 40 degrees. And let's see, it'll work out at 4.5 and that works out at 5.36 meters per second. Right, so the total time of flight, we can work that out because we know we can work out the time it takes to get to here, because we know at this point u equals 7 meters per second and at this point v equals 0 meters per second. So v equals u plus at. I'll do it down here, so that'll be 0 equals 4.5, and this at, because this is going to be decelerating, it's going against gravity, so this is going to be minus 9.81 t. So therefore we just rearrange that and that's going to be minus 4.5 equals minus 9.81 t. So t is going to equal minus 4.5 divided by minus 9.81, which equals 0.459 seconds. You see that there? Right. And if that's your time of flight to there, so to get to there it's going to take double that. So the time of flight equals 0.917 seconds. Okay. To find the maximum height, we know when it gets to there, we know that the V equals 0 and U was equal to 4.5, and so that's 0, that's 4.5. We know the deceleration, or the acceleration due to gravity, and we want to find the distance, so we'll use this equation here, v squared equals u squared plus 2as, because we've got that and we're wanting to find this. So we'll plug those values in. 0 equals 4.5 squared minus 2 times 9.81 times s. So again, put this across the other side. 4.5 squared minus equals minus 19.62 s. What's that? 4.5 squared s 20.25 equals, I'll bring that down there, minus 19.62 equals s. So therefore s equals 1.03 meters. And this is a golf ball, isn't it? I don't know, he's not exactly got very far with this, I don't think. Well, let's see how far he actually gets. So he's whacked it and he's got up to 1 meter height. Right, so let's see how far he goes, let's see what the range is going to be. So the horizontal velocity was 5.36 meters per second, and the time of flight was what was it? 0.917 seconds. So distance travelled equals velocity times time. 5.36 times 0.917, which equals 4.92 meters. So he scalped the ball, or whoever scalped the ball, it's went 1 meter high and it's landed just shy of 5 meters away from the person. I think they need to get a little bit of practice in, if you ask me. Right, we'll go into question 2 now. Right, this one here, you've got a weight there, 3,000 kilograms, and it's getting accelerated up this way at 0.5 meters per second squared, and it's getting accelerated down this way due to gravity, 9.81 meters per second squared. Right, and this effect of pulling this rope here or wire, it causes a tension in the wire, and that is the kind of net tension, the net forces that are left acting on this wire. The way I kind of look at this is, if you're holding this and you let it slip through your fingers a little bit and let it accelerate down the way, or if there's a force acting down the way, as if it was accelerating down the way, it lessens the tension in the rope here. And what's happening here is this is getting pulled up the way at 0.5 meters per second, and it's got a force going pulling it down this way at 9.81 meters per second. And the way I tend to look at this is the net forces of acceleration acting on that tension would be 9.81 plus 0.5. That's because this is pulling that way and this one's pulling in that direction. So the 9.81 going this way, you're going to add this. So now say you were dropping this, at 0.5 meters per second. The force would be acting in this direction. So therefore you would subtract that from that, 9.31, and up here we're going to add this 0.5 to it, so that's going to be, what's that, 10.31. And to find the tension in the wire, just simply multiply the 3000 times the 10.31, and that's going to equal 30.930 newtons for that. Now what I've got written there, actually, if this was a static, say that wasn't moving, the force of the mass times the gravity here would equal the force and the tension, the tension in the wire, if that was in a static situation. So you could write it like that: the mass times the gravity is equal to the tension, or like that if you preferred. And then this force here upsets the balance, upsets the static, and causes an acceleration and turns it into a dynamic situation. So hope I've not overcomplicated that one. Right, this one here, we're pulling this block along here on a surface, and it's moving at constant velocity. So the only force we have to really worry about is the frictional force here, and we're pulling it along there. So the frictional force you have to overcome is this friction here where it meets the surface. The coefficient of friction is 1, so let's work that out then. So the frictional force, equals, if it was 50 kilograms, yeah, it's going to equal this coefficient times the force of mass times the gravity, which is going to equal 1 times 50 kilos times 9.81, which works out at 490.5 newtons. Because this is going at constant velocity, that means frictional force is going to equal the tension. So tension is going to equal 490.5 newtons. Right, so in this example, because this here is flat on the surface there, the only that's like the mass and the gravity is kind of contained in the friction there. That's only kind of force with regards to friction we're interested in. But in this next example, in this next one, we have to take into account the block here of the friction caused by the contact with this, just kind of like before, and it's the same coefficient. Remember, if that was like a half, the last value there would have been a half, because it would be more slippery. That's what that was the coefficient there, as an indication on how well the material allows other material to slip or move across it. Right, and also, right, so we're going to have a tension in this rope again, and also we're going to, because, so same with the last one, it was, the block was sitting here, so there was no, so the gravity was acting in this direction, but up here there is a force caused by this angle, this incline, caused by the force of gravity on that incline, want to push it down this direction, so we have to take that into account as well. So we'll call that the force of, we'll just call that the force of its weight, let's see, we'll call it that, and this is G. Right, so this force here, F W, is going to be, and remember we have to take your components again because this is on an incline. Right, what I want to try and make clear here, if I can, is if we're looking at this block on this incline, right, the force of gravity is kind of coming down like this. Yeah? Now, because this is on an incline like that, and this will be at the same angle, so we get to this, so this will be, I always kind of visualise it like this, and this slope is kind of like that. Like my rubber. Now, if this was which it is, a right angled triangle, 20 degrees, this would be the adjacent to that angle. So this part is going to be mg cos theta, and this part going down the slope is going to be mg sin theta. I hope you can see that. It can be quite confusing to try and visualise that on yeah, darling? Wait a second. Right, so we'll call this FMG for where it touches the surface there, and it's going to equal mg cos theta, but this friction force then is going to be F friction is going to be the constant, the coefficient, times mg cos theta. Right, and through the F, the mass will be mg sin theta. That's this one coming down here, and this is the force there connected with the friction associated with this part, and the tension is just going to be the sum of these two. So the tension is going to equal, wait a second darling, right, and you just simply add these, so that will be 1 times 50 times 9.81 times the cos of theta, that's that, and then plus 50 times 9.81 times sine of theta, which is 20, and that works out at 460.9 plus 167.8. So the total is 628.7 newtons, and the difference between that and it being flat was what was it, 490.5, so the difference is going to be, that minus that is 138.2 newtons delta T. Oh, can you see that? I hope that makes sense. And we'll go on to the next question. Question 4. Right, we're wanting to find the moment of inertia for this. Not very well drawn axle there. Bit off balance. It's very similar to the question in the exam actually last year. Right, we want to find out, firstly we want to find out the volume of this, and then use the density and to find out the mass. Right, first things first, let's see, this one here, so that's 77.5, is like the width of this, and we want to multiply that by the area of this part here. Right, what's that? 4.06 mils. What I'm going to do, in fact, I'm going to change all this to meters, because we're going to be working in meters. Right, so this width here is going to be 0.0775 meters, and this diameter here then is going to be the diameter 0.406 meters. Right, now to get the area of this, you could half that and use pi r squared, or you can use pi d squared over 4. So because we've got the diameter, we'll just use that then. So that's going to work out at the volume of the wheel here. I'll call that, and that's going to equal pi times 0.406 squared divided by 4 times, can you see that? Yep, 0.0775, and that's going to equal 0.01 meters cubed. And find the units, eh? If that's meters squared times a meter, it's going to be meters cubed. Anyway, it's a volume, of course. Right, the next part, the axle. The part of the axle we're looking at is this and this part, because we're assuming that this part of the axle is made up, included in this part. Right, so what that's going to look like is the axle is going to be the same again, pi times the diameter here, which is going to be in meters again, so that's going to be 0.0352, if that's in meters, that's squared, divided by 4, you see that? Divided by 4 times, right, now that whole length is 341, we're going to have to subtract that from it, which is going to be, let's see that, 0.341, and that will be 0.341 minus 0.0775, so that equals 0.2635, and that gives us a volume of 0.000256 meters cubed. So the total volume is going to be both of them added together, 0.010256 meters cubed. There we go. Last then is going to be the density. You see that? The density times the volume. Well, we must be given a density somewhere. 8600 times the volume, 0.010256, and that's 88.2 kilograms. Good stuff. And the radius of gyration, I mean the moment of inertia I equals mass times the radius of gyration squared, 88.2 times the radius of gyration is 0.168 meters squared. So that works out at 2.49 kilograms per meters squared. Now this one here looks complicated, but it's just about transposition really, and here it gives you all the values to put in here. Pretty much you get your height from there, and it's basically just a case of rearranging this now, and we're looking for I here, right? And this is your potential energy, the kinetic energy of the falling block, the rotational energy, kinetic rotational energy of the flywheel, and then this is your frictional losses, the work done against your friction, and this is just a ratio that they use to determine how much friction there is. Right, so basically just rearranging this. So what I would do in this situations, I would get rid of these 2's. So the 2mgh equals mv squared plus I omega squared plus I omega squared n1 over n2. Next, that is my daughter's rubber, by the way, in case you were wondering. Right, and 2mgh equals mv squared. But what I would do is I would take the common factor out of here, which is going to be omega I, take I out, plus omega squared n1 over n2. Then I would kind of shift this over here. I would go I omega squared plus omega squared n1 over n2 is going to equal 2mgh, and I'm going to subtract, I'm going to move this to that side, so I'm going to subtract the mv squared from there, and then I is going to equal 2mgh minus mv squared divided by omega squared plus omega squared n1 over n2. Can you see that right? My pen's getting a bit blunt. Pencil, I mean. 2 seconds. So then we just need to plug the values like that. So that's 2 times 5 times 9.81 times 1.4 for the height, minus 5 times 0.095 squared, all divided by omega squared 4.3 squared plus 4.3 squared times 10 over 14. Oh, I hate a bracket. Right, and that all works out at 4.3 kilograms per meters squared. Cool. Right, we'll move on to this next one. What is it? Determine the impulse when the mass strikes the floor. Is it linear or angular? Right, the impulse is your change of momentum from your final momentum. You subtract your initial momentum. Impulse mv minus mu, your final momentum minus initial momentum. Right, and there's another way of kind of looking at this. Like, see if you're going at 30 miles an hour in a car crash, it doesn't seem like you're going very fast. Or see you're going at see the force you were going to exert on something. See, you're in the car crash and you were to have a kind of instant force that happens in a quick. So see, I had a force of say 10 newtons, say, right? But this force was applied, this 10 newtons was applied in a change of time that was very small. So say you're a force of 10 newtons, but that's applied in 1/10 of a second. That means the force you would experience would be 100 newtons. And that's why if you're in a kind of crash or something, or you get hit with something and the actual contact time is very small, the force is magnified. Anyway, that's another story. But I'll just quickly do this one. So that's 5 times its final velocity minus, well, its initial velocity was 0, so that's going to be 0. So that's 0.475 kilograms. And just for a second. Right, and the last bit, you want to work out the power here. Right, oh, and I forgot to say, because this block's dropping in that direction, it's going to be linear. Right, and to finish this one off, number C, the frictional torque. Right, so we want to work out the energy, then work out how much power that would be in 24 seconds. So the energy is going to be frictional torque, and it gives you a value of 0.345 Newton meters per revolution. Right, so we always work in radians, so if you divide that by 2 pi, that gives you, actually gives you the energy per revolution, right? So then if you want to find the total out, so it's, what does it say, 10 revolutions, right, it's going around 10 times, so that is going to be, that is 0.05494, say, it's quite a small number, so I'll keep these going a bit, then times that by 10 is going to be equal 0.5494, say, and then, so that's in joules, and what is it saying in 24 seconds? So the power equals energy over time, so that's 0.5494 divided by 24, which comes out at 0.0229 watts. Good stuff. I think that's right. Please get in touch with me if I've made any mistakes. Okay. Right, and now the last question. This last question's just getting you to do the sketch the graph thing, the velocity time graph, and then obviously the area underneath the graph is the total distance you've travelled. Just a quick thing actually. Here, if you have a velocity time graph and where the velocity is changing here, or if at this point it's kind of level, it's not changing, that means there's like no acceleration, or here or there's a deceleration and here's an acceleration. And if you've got the velocity and this is your time, and you want to find the tangent of this, in other words the gradient of this at any point, you just use dv by dt, and if you want to find the area, say from t1 to t2, you would integrate velocity with respect to time. That's just a quick note that, and that allows you to kind of analyse any velocity equation really. And so that's the acceleration, that's your distance travelled. Anyway, I suppose you can actually see that when you see, if you look at v equals u plus at. If you were to integrate that, oops, that looks like an f, you get ut plus, to integrate that you'd put 2 up there and you'd put a 2 there. Ut plus half at squared, that's where that comes from. And obviously if you were to differentiate that, you're just going to be left with a. Right, anyway, just a wee footnote. People always wonder why you use calculus, and it's good to have a kind of an idea of that. What's that, darling? I'm okay now, honey. I'll see you in a wee bit. Right, so we're going to make this graph my daughter's ruler as well. Something like that. Time. I'll just quickly, because I could do some lunch. Right, so it accelerates, so it starts at rest, accelerates for 10 seconds. Right. And what we're getting is it accelerates up to 13 kilometers per hour, which is no good to me. I want that in meters per second. Just can you see that? So that equals 3.6 meters per second. So this accelerates, so let's just say 10 seconds, and this accelerates, I'll just say 3.6, something like that. Right, I was at constant velocity for 1.5 minutes, that's 90 seconds, 1.5 minutes, and it's constant velocity, so this will be going up to like 100, so 100, so it's going to look like that. Oh, got a ruler, why don't you use it, Gavin? You see that? Right, that's going to be a triangle, and this is going to be a rectangle, and then what's happening here, accelerate for another 5 seconds at 6 meters per second. So the velocity is going to be v equals u plus at, which is what, 3.6 plus 5 times 6, because it accelerates for 6 seconds, no, it accelerates for 5 seconds at 6 meters per second, that's right. So that's equal to 33.6 meters per second. So this is going to go from here, 3.6, so I'll say it's up here somewhere, and it's how many seconds? 5 seconds, so it's only a wee bit like that. Because this is, I'm going to have to sum all these and put them into their wee sections. So what did I say? 30 odd, up here somewhere. I'll put it above there. So this will be going up like that. So there's going to be this kind of triangle. I'm going to have to, and then so what happens now, constant velocity for 2 minutes, 120 seconds, so this is 210, oh sorry, 105 this is actually, so it's 120 seconds, so it's going to go up to something 225, right, and then I'm assuming he's going to stop at some point and come to a stop at a rate of 2.5 meters per second. Right, so we've got an initial velocity and a final velocity somewhere down here, right? So again, we'll just use v equals u plus at. V equals u plus at. Final velocity is 0. Can you see that? Yep. The velocity here was 33.6. So 33.6. Now it's decelerating at 2.5 meters per second. Is that right? Yep. So that's minus 2.5 times the time. And when you rearrange that, it's going to be minus 2.5 equals minus 33.6. So t is going to equal minus 33.6 divided by minus 2.5. That's equal 13.4 seconds. So add that onto there. What's that going to be? 238. Over there, something like that. 238.4 seconds. Got a quick journey. He didn't even stop till we got to the end. Anyway, right. So now you just add up these areas. I'll just quickly do that. Right, quickly done that, and the total distance then is just going to add all them together, and that works out as st displacement t equals 4694 meters, or 4.69 kilometers. Whatever floats your boat. Right, and now we've got a couple other wee bits and bobs to do here. Right, so we have to work out the angular displacement and the second part of the acceleration, and looking at the graph here, that's this bit here. Oops, here. That's this bit here, 75 meters, right? And the radius, so it's got 200 mil diameter, 0.2 meters, so radius is 0.1. so the angular displacement is going to be the distance travelled divided by the radius of the wheel, which is going to equal 75 over 0.1, so that's 750 revolutions, or radians actually. Yep, that's radians. Okay. Oh, there's another wee bit in fact. What's this? We have to work out the angular, or the RPM of the wheels, right? The velocity, what the first constant part was, let's see, it was 3.6, that's right. Oh, 3.6. Right, again, the angular velocity is equal to the velocity divided by the radius, 36 radians per second, and to find out the RPM we multiply this by 36 times 2 pi over 60, which equals 3.77 RPM. Okay, I think that's us. Hope that was of help, and I'm going to send you another tutorial with a bit harder, the questions are going to be a bit harder on dynamics, and that should be enough to cover what the questions that are in dynamics. There's a couple of them that are quite complicated, so a bit more involved, but we'll get into them in this next tutorial. There may be like 6 quite hard questions, and after that we can draw a line under dynamics, because we'll be ready for whatever the graded unit could throw at you. Anyway, thanks for listening, cheers, bye.